Hello and welcome to a new lecture of classical motion of a single particle. In this lecture, we will start a new topic, that is the motion of a particle under different constraints. In nature, if you see that if we do not specify anything else, then when we say that a particle or a point particle is moving in one dimension, we imagine that the particle is moving in a straight line. Okay? Or just for example, if we say that the space has dimension 2, that means the motion is now 2 dimensional, then we just think that okay, now the particle will move in a plane. That were the cases respectively for the uniform motion, where the particle is constrained to move along a straight line, because the only dimension possible was 1. Okay. Now, another possibility, another case was the case for the central force, where the particle moves in a plane, because then we can show that the conservation of angular momentum compels the particle to move in a plane, and that plane is the perpendicular to the angular momentum. Okay. Now, this comes from the very basic nature of the force, okay, for the central force case. In a 3D, if we also say that a particle is just moving, then again the particle can move, I mean in any way in a 3D space, okay, wherever it wants it can go. Okay. Now, under certain circumstances one can wish to impose some limitations on the motion of the particle, and those type of limitations should not come from the basic nature of the force, but it should come from the basic geometry of the kinematics. Okay. If we have this type of limitations, then we can actually call those limitations as constraints. Okay. So, we will try to make some examples today, and around those examples we will try to discuss the concept of constraints. Okay. So, we will make some concrete examples in today's lecture, and around those lectures we will try to understand how constraint motions are taking place in nature, and how according to the different nature of the constraint forces we can differentiate or classify different type of constraints or different type of motions. So, constraints are the limitations or conditions imposed on the kinematics of the particle. Okay. So, if I now say that okay, I have a particle, okay, the particle will move in a 3D space. So, for example, I can draw a 3D coordinate system, okay, x, y, z, but I will still say that the particle will always move in a line like this, okay, in a curved line. Okay. So, for example, the particle cannot move here or here, but after some time t from its starting point it should come here and then it should come here. Okay. I can do the same thing for a circle or a sphere even. So, let us say I have a point particle and this is a sphere. So, now again the sphere is in 3D, but then I say that the particle is moving on a sphere which is having a rigid surface. So, the particle cannot go inside the sphere. Okay. So, and the particle also cannot lose contact of the sphere, then the only possibility is that the particle should move on the sphere, always making a contact, okay, with the sphere. So, a very well known example for such type of constraint takes place when we are considering our motion on the surface of earth. So, every time we are actually moving on the surface of earth, and we do not in general want to lose contact, okay, otherwise we will fall down. Okay. So, you will see that So, this is a case where a particle is moved a particle is moving on the surface of a sphere. Okay. I can make other type of constraints. So, here I can say that okay, the trajectory will be such type of some equation of a curved line in 3D space. For this the constraint is simply that if the particle has at any instant the Cartesian coordinates to be equal to x, y, z, then the condition for which the particle will be exactly at the surface of the sphere will be x square plus y square plus z square will be equal to r square, where r is the radius of this sphere, okay, and that is actually a constant. Okay. If we think that the size of the sphere is constant in time, we can generalize this a little bit more. We can say okay, the particle should always move on the surface of the sphere, but now the sphere is changing its shape, always being sphere, but it just increases or decreases its radius in course of time. Okay. Following some law which is an explicit function of time. Let us say we can say that okay, r is equal to alpha t, where alpha is a constant. Then what happens that when the sphere is this one, okay, or this one, for all the cases your x square plus y square plus z square will be equal to r square, but this r square is now no longer constant, it will be alpha square t square. Okay. I can make a little bit modification in this whole set of examples with the sphere, is that I want now a particle to move exactly inside the sphere, but without touching the surface of the sphere. So, that means for example, let us say the inner surface of the sphere is coated with some material which absorbs the particle, okay, and it is a glue type of thing. So, once the particle just touches this surface, okay, from inside, so it is actually glued or stuck to the inside part of the surface. Okay. Then in order to survive and continue its motion, the particle should not touch the surface, but the particle should be always inside the surface because the surface is rigid. How to then impose the constraint? Then the constraint should look like this, that for that particle the x square plus y square plus z square will be strictly less than r square. Okay. And this is also true whenever this sphere is actually changing its shape with time. Okay. I can do the other way around as well. I want a particle which should actually be always outside the sphere anywhere. Okay. I do not have any problem, but this particle should not touch the sphere. Okay. Let us say I have now a particle outside P, okay, and here on this outer surface of the sphere, okay, I have made some glue type of material, and whenever the particle touches the sphere, it is stuck there. So, it will be lost and it will not continue its motion, and that is why, okay, the constraint will be here x square plus y square plus z square will be strictly greater than r square. Okay. If there is no glue, okay, then the particle which was inside the sphere could actually move inside the sphere and also could touch the sphere, and the same thing for the particle outside the sphere, that it could move and also eventually it can encounter the surface of the sphere and will bounce back. Okay. It is possible, I mean, whether it is bouncing back or it is I mean exactly just take some time, that will depend on the proper nature of the surface. Let us say this surface is rigid, so the particle will eventually bounce back and there is no glue. So, we can then say for these last two cases we can use this type of equality as well. So, x square plus y square plus z square will be less than equal to r square, and in the second case it will be x square plus y square plus z square greater than equal to r square. Okay. We can also think of two very useful example which will be actually used in our discussion, that is the case of a pendulum. So, simple pendulum. So, we said that this is a very popular example. So, I can draw a string of fixed length and a mass bob, okay, of mass m is hanging from this. The string has a length L, okay, and this point is considered to be the origin of the coordinate axis. So, I can just say at any instant of time okay, let us say the particle is here or the pendulum is here, the bob, okay, or the particle is here, let us say. Okay. In all these possible positions, okay, the only one constraint is that the length is fixed, L is fixed or constant. Okay. If this is true, then if we say that this motion is taking place in an xz plane, okay, and z axis is, I do not know, for instance we can take z axis to be okay, I can just take like x like this and z like upward, okay. So, z, so it will be all this z should be here, every z should be negative. And so, for example, if the particle is here, its z coordinate is actually minus L. So, z will be minus L and x coordinate will be 0. Here it would have some other coordinates z and x, and that will be given by the angle theta. Okay. But whatever be the coordinates, one thing should be clear, that at any possible position, if the length of the string is not changing, then x square plus z square should be constant, is equal to L square. So, you see that we have a condition on the length of the particle, okay. And when we say this is a condition or a constraint, this is a condition on the length of the string, okay. And this is actually synonymous of saying that this is a constraint on the position of the particle. So, if the length of this string is a constant, then of course, you will understand that if you add all possible positions of the mass bob, they will just create an arc of a circle of radius L, okay, and that is exactly is manifested by this equation. Okay. So, now we can move a little bit forward, and by saying we can sophisticate the case by adding some flexibility to the length of the string, but we now say that this length will be not a constant, but it will be simply a function of time, let us say 1 plus sin omega t times L0. So, at t is equal to 0, this is 0 and L is equal to L0, maybe that is the length, and when t changes, okay, according to that actually the length changes. So, that means you will actually have a situation where you can have a bob which is like that, but then at some other instant it can actually have a shorter length, and here. So, actually you will see that this is, so if we just take this one, this formula. So, when t is just increasing, so from 0 to some angle, so let us say the angle is small, but it is actually increasing with time. So, actually L should increase, okay. So, if L should increase, actually you will have a greater length like this, okay. And then even a greater length over here. Okay. So, now if you just try to add all these positions by an imaginary curve, it will no longer be an arc of a circle of fixed radius L, right, that you can easily understand. So, this is an example where we can have a constrained motion. Okay. Finally, I will take the example of another one, which is the second example I will be using throughout our discussion. That is the example of a particle which is moving down a inclined plane of some, let us say, constant angle theta, okay, and a particle is moving. Okay. So, let us say it is like a hill, and from the top of the hill, so let us say this is H, okay, and from the top of the hill the particle starts moving from rest, and after some time it is moving, but when it is moving actually, okay, we are imposing the condition that the particle should always be in contact of the inclined plane, and if we do that, then this is a constraint on the particle. Okay. And if you actually do this type of thing, then you will easily see that how will be the constraint expressed. So, of course, you can easily understand that if again this is x direction and I can talk this about this axis to be the z direction, okay, then every time if you have some x coordinate, let us say for the particle x and z, and here x and z, okay. So, whenever you take its x coordinate and instantaneous z coordinate, you will understand that will simply give you, so z by x will be equal to tan theta, okay, and this tan theta is a constant. So, actually what you will have, so let us say I just call this as alpha. So, z will be alpha x. Okay. So, again you see that this is a constraint on the position coordinates of the particle. Okay. So, you see that this type of constraint can also be a little bit made a little bit more flexible. So, let us say now this inclined plane is no longer a rigid inclined plane, and this is made up of ice, let us say, or some material which can actually destroyed or can be damaged, okay, with time. Okay. So, let us say there is a landslide which is going on, and some particle which was starting to move from a very high point of a hill, when it starts falling, okay, let us say that these parts will actually changing its shape, okay, and when it changes its shape, then what happens that the particle will actually no longer move in just a normal straight line like this, but it will now move in a little bit non-trivial way. Now, if I again put this condition that we have to now find the motion or the kinematics etc. for the particle, if the particle always remains in contact with this surface of the hill, okay, and that is actually, you will understand, that is a very non-trivial problem, because the hill's shape would change in a very random way. You do not know what will be the law of landslides. So, you cannot really predict that what will be the you can somehow predict globally from its structure and calculating other constraints and everything the engineers can do, but from a physicist's point of view this is a very non-trivial problem, because you are not sure that this is a little bit more sophisticated even from this problem of this pendulum with variable length, because here you always know that the pendulum is changing its length, but it is always a straight line. Okay. Here the point is that you do not know whether it will be remaining a straight line or a good curve where you can do some mathematical analysis. It may or may not be. But if I then say the constraint will simply be that the particle will always be at the contact of the surface of the hill, then you have to actually put a constraint appropriate to that condition. Okay. But that constraint is a little bit more tricky and cannot be simply written in a line. Okay. Now, after talking all these things, we can see that we can have actually basically various types of constraints, and the constraints which I just talked, they constitute more or less the most of the familiar or the usual examples of classical mechanics. So, if a constraint is such that the constraint is independent of time, okay, explicitly there is no time in the expression of the constraint. For example, the system with this simple pendulum with a string of constant length. This constraint has no time involved in this, okay, or this constraint where the particle was supposed to move on the surface of the sphere with definite shape. Okay. So, again this is a constraint where you cannot see time appearing explicitly. Okay. Those constraints, so I can now write some vocabularies. So, vocabularies the constraints without explicit time dependence is a scleronomic constraint. Okay. Look at this constraint where the particle is moving on the surface of the sphere, but the radius of the sphere is an explicit function of time. Okay. So, in this constraint you can see time is appearing explicitly. Okay. Or here where you have L square is no longer a constant, but L square is simply L 0 square 1 plus sine omega t square, which is an explicit function of time. Okay. This is the case for this pendulum with variable length. Okay. If you have this, then you have the constraints with explicit time dependence. And we talk of a rheonomic constraint. Okay. Number 3. Okay. I change the color of this. You see, some constraints are equalities. Okay. You see that this equals to this equals to this. Again, some constraints are not equalities, they are inequalities or equality inequality combined, but whenever there is a strict equality, for example here, here or in these two cases, we call that a bilateral constraint. So, yeah, constraints in the form of equations, bilateral constraints. Okay. Now, if the constraint is in the form of inequality or it has a mixture of equality and inequality, in both cases the constraint including inequality is a unilateral constraint. Okay. So, these 4 vocabularies are very interesting for you, but now I will go to introduce 2 important vocabularies which will be of surmount interest for us. The first one is the holonomic constraints. I can write number 5, holonomic constraints, and number 6, non-holonomic constraints. For these 2 I first write their name and then I explain what they are. Non-holonomic constraints. Okay, I just put it singular, yeah, constraint. Okay. So, holonomic constraint is a specific type of constraint which is expressed in the form of an algebraic and sometimes even trigonometric or exponential, etc. That is no problem. If you integrate, it is good. An algebraic, even a trigonometric, exponential, equality, and contains only coordinates, that means position coordinates, and time. Okay. So, of the examples which I discussed here, this one, all are holonomic constraints. Okay, all are holonomic constraints. Even the first one, this is also holonomic constraint where you have this one. For the second case, we associated with this inclined plane. This is a bit tricky and we even do not know how to model, but if we can write in a proper manner smartly in the form of an algebraic form with this change of shape, then of course it will be another holonomic constraint. What is a non-holonomic constraint? So, non-holonomic constraint is, for example, all the unilateral constraints, that means constraints involving the inequalities, and constraints involving the velocity coordinates. A special comment is that and can never be integrated to a holonomic constraint. What is the meaning of the last sentence? I am coming to that. For example, I say that for the movement of a particle in this inclined plane where there is no corrosion or no landslide, I know z is equal to alpha x, but of course I can equivalently say that z dot equal to alpha x dot, but this is an equality, this is without any explicit appearance of time, but this is a constant where only you can see velocity coordinates are appearing. There is no position coordinate, no time. So, can it be holonomic? The answer is yes, because this is called a pseudo holonomic constraints, because if you integrate this, it will finally give you z is equal to alpha x plus c. Now, c you can get rid of by choosing initial conditions appropriately, suitably. So, in case you have this type of thing, then this is not a non-holonomic constant, this is a holonomic constant. Let us say I give you an example, x dot equal to alpha x y. I say that the motion of a particle is such that, let us say in a plane x y, that its x dot that is the x coordinate of the velocity is proportional to x y, that is the product of x and y, then you cannot integrate. So, it cannot be integrated to f x y all these position coordinates, let us say for 3D x y z and t is equal to 0. Okay. So, that is why this is non-holonomic constraints. In this occasion I actually have written the general expression for a holonomic constraint. So, the general expression of a holonomic constraint is that you can always have a function which is involving x, y, z and t, that is the most general case possible in 3D space, which will be equal to 0. That means there will be a equality. For example, if you have x square plus y square plus z square is equal to L square, then of course this function will be x square plus y square plus z square minus L square is equal to f x y z, and that will be 0. Again I am taking the case for this pendulum. So, x square plus z square is equal to L square. So, pendulum of fixed length. So, you will have x square plus z square minus L square, which will be now the x, z and x and z, and this is 0. So, finally, pendulum with variable length pendulum with variable length, you can actually write x square plus z square, the example which we all have already discussed, L0 square times 1 plus sin omega t whole square. Now, then the function will be is a function of x, z and t, but that will be x square plus z square minus L0 square 1 plus sin omega t whole square will be equal to 0. So, now you see that for any holonomic constraint you can always have this type of form. So, in the next lecture we will discuss the importance of holonomic constraints and how using those constraints we can actually think of formulating a very easy way to solve different type of usual problems of classical mechanics. Thank you.